Okay, thank you very much, Dave, for giving me this opportunity to present at this large group. And thank you all sitting for this presentation. Estimating crystallization pressures of granites. And we are going to talking about analysis of equilibrium, consideration redox conditions, and texture aspect and the emplacement processes with implications for metallogenesis. Yeah, before I start, I thanks all those pupils helping me to understanding the system, including Dave Lenz, Guoxiang Qi, and Nelson Amby, and Professor Li Xianghua. And also I thank the colleagues from the Manitoba Geologic Survey, especially Christian Baum, Tanya Martins, and Chris Koslan. Yeah, today I'm going to talking about at the first phase equilibrium about the haplogranite systems. And then from there, I created a quartz geometry using the quartz normative composition to estimate the granite crystallization pressure. And the problem of that, this geometry is evident because there's various components are not considered in this parameter. And then I propose practical new procedures to estimate the ferrous iron oxide ratios, how they affect the geobarometer. And then I briefly touch a little bit textures and emplacement processes and implications for the granite intrusions. And finally, I will conclude with a few message taking home. This diagram just shows the granite, related or partly related gold deposits at various forms of depth, from very deep, like greenstone host gold deposits, to the intrusion-related gold systems, to porphyry, and to the epithermal. And from the depth prospect, you can see some of them are related with the granitoid intrusions. If we know the depth of the intrusion, we definitely know what how depth of the gold deposits genetic to the granite intrusions. So we know for this is important for the mineral exploration prospect. So we can design our drilling program, how deep we can target it for the minerals. And the other things we also know, the different deposits are related with different types of the granitoids. So far, there's many ways to estimate crystallization pressures, like geological mapping to reconstruct the stratigraphic column overlying on the granite intrusions. This is pretty time is consuming, but is very useful for the survey or companies. Other things, we use the petrological studies of the contact metamorphic rocks around the granite intrusions. That is derived from the aluminum in the hornblende diabarometer. And some people use that also just to analyze the hornblende in the granitoids to estimate the hornblende crystallization pressure. And we're also using the geochemical 3D geophysical imaging to configure the intrusions. But the geophysical surveys method is reflect the current status It cannot know the depth of the granite intrusions formed at that time long ago. And we also can use like fluid inclusions. I mean, that partly reflected in a hydronic rather than lithostatic pressures. And a group of people built a rhyolite melts modeling in terms of the phase equilibrium and also the water and the CO2, a mix of models to model the crystallization pressure of the felsic granite intrusions. And the most successful, I think, is the experimental petrology to simulate, the conditions of the PT, X, and water conditions for crystallization pressure conditions. And now I'm talking about a little bit, focus on the phase equilibrium. And Norman Bowen published his classic textbook, The Evolution of Igneous Petrologies, that has established the foundation of the modern experimental petrology. It also pointed out that the origin of the granitoids are magmatic, informing the view of the James Hurden's viewpoints, because there's a lot of argument about the origin of the granitoids. Ever since Bowen and his students established the Hopler granite systems, that is the foundation of modern granite petrologies. And this is the phase diagrams, and it is a projection from the water packs to the quartz arbide and orthoclase base. And at the different pressures, you can see the quartz crystallization with one feldspar. With the increase of pressure, it until go to the eutectic point at about 5 kilobars. At that time, the quartz co-equilibrium with the 2 feldspars. And from this diagram, we also see the higher of silica content of the granite melt, the lower crystallization pressure of the crystallization. So based on the existing experimental data set, I get a very interesting curves about the, I called the quartz geometry or geometry, and that correlates the crystallization pressure with the normative of quartz. There's a beautiful curves that can be described by a polynomial function. You can see the highly equate, correlation efficient is so high, and when you plot on these things and do the calculation of your samples, granitoid samples, to the CIPW normative calculation, and then you using this function equation, you can immediately get the pressure. And there's another complementary equation with the arbite and orthoclase also have the same coefficients. And you can do this very easily, and is numerical. But also, if you want approximate estimate, you just plot your data on this diagram, you can get to the estimate of the crystallization pressure. And this is can be used the range of the quartz concentration between 40 to 15 to 40 to 14 percent. And then other things, when I compared with using the quartz barometer and also correlated with the Humboldt aluminum in Humboldt geometer, you can get nicely a linear correlation line. And this the dashed line basically is the aluminum in hornblende parameter equals the pressure estimated from coarse parameter. And when the pressure towards 600 MPa or 6 kilobars, these two methods get the pressures approach that indicate the hornblende may have crystallized earlier in the history of the granite crystallization. The problem is, as I mentioned before, is this barometer only considered silica, aluminum, sodium, potassium, water, and not considered calcium and iron oxide and other component. And this talk, I focus on the redox conditions, how they affect the estimated result. And we use the ferric iron number, that is Fe3 plus number equals more molar ferric iron oxide ratio. And this ratios actually is reflect conditions, redox conditions, and that controls the formation of all deposits associated with granite intrusions. I will talk this later. And then we use the few type samples to test how the ferric iron number affects the gyrometer. I tested the metaluminous to a per aluminous granitoid rocks, and also tested per alkaline granitoid rocks. And this is the diagram just showing the oxygen fugacity and the redox, the relations with the temperatures. You can see the I-type granites magmas are usually very high oxidized, but for S-type, the granitoid magmas is below the firelight magnetite quartz buffer is reduced. And you can see the porphyry copper deposits usually is very high oxidized, but the intrusion related gold systems usually be pretty reduced. And also the like a porphyry silica, I mean tin deposits is also related reduced magmas. And we use selected samples that is well constrained by the experimental work or the petrography work to constrain the mineral composition, I mean assemblages. And the sample we used, many taken from these references. We plot it, and you can easily see the granites range from the alkaline to like a calcic or alkaline, alkaline, per alkaline. And this is based on the Riemann series index method. And also you can see the red line, that is the curve subdivision, the sub-alkaline, the alkaline series of volcanic rocks defined by Irvin Barraga in 1972. That is mostly overlapped with a line of sigma equals 3.5. And below that is the sub-alkaline, and above is alkaline rocks. And also we use the aluminum saturation index. You can see the some samples belong to the per-aluminous, some is the metaluminous, and some is moderate. And a few samples from the per-alkaline field. And then we use this data to test how the iron ferric iron number affect the pressure crystallization crystallization pressure estimation using the quartz gyrometer ladder. And here I use the quartz diorite sample, and you can see I use different numbers, the estimated pressures beautifully with increase of the ion number, the pressure will follow this line, a curve, and also this can be described by a polarimeter. And the thing is, when you can see the number 0.1, you got high pressure, and they got 0.7, you got lower pressure, and the difference of the highest and the minimum pressures as large as the 437 MPa. That is well beyond the uncertainty of the quartz geometer. And this is the second for the metaluminous granodiorite samples. And you can see the difference of the highest and lowest pressure estimation is 44, is still pretty young, I mean, pretty large. When you see ferrosic granites, and the difference between the highest and low pressure estimation is pretty low, and 22 MPa is almost the same within the uncertainty of the geometer. And this for the per aluminum, per alkaline solid amphibole bearing granitoids, you can see the highest estimation and the lowest is very low. And also for this, a little bit silica content lower, per alkaline solid amphibole bearing granitoids is 30, is almost marginal within the uncertainty. I didn't mention the error of the two equations described before. That is 16 MPa. So how we can get a good estimate the ferrous iron oxide ratios, because the modern geochemical whole rock data usually only provide the total iron oxide, either is ferric iron or ferrous iron. But how can you get, you know, the ferrous and the ferrous ferrous iron oxide ratios? So you need some estimation. So this is actually was published this year in an ethos, and the co-author with Dave and Guoxiang. So we propose 5 steps. The first, we were looking why we're using this procedures. One, determine alkalinity of the granite samples, step 1. And then we calculate the ferric iron ratio, and then convert the total iron to and adjusted ferric and ferrous values in terms of calculated of the iron ratio. Using this and adjusted the ferric and the ferrous values to compute the CIPW normative compositions, and then we calculate the granite crystallization pressure using the barometer. And as I mentioned before, they're using the Riedemann series index and to determine the alkalinity of the sample. And if the value is larger than higher than 8.8, then it may not to lead to calculate the iron ferric iron ratio, a number, because the granite is per alkaline. And then we can go to step 5 directly using the barometer to estimate. And if the sigma value between 3.5 to 8.8 is alkaline or less than 3.5, so we go to step 2. And I mentioned that when the sigma is equal to 3.5, that is overlapped mostly with the boundary of the subalkaline and alkaline rocks. suggested by Irwin and Barraga before. And the step 2 to calculate the ferric ion number. And here we have some assumptions based on the iron titanium mineral assemblages. Oxygen fugacities are assigned as the following. Log of oxygen fugacity larger than delta ferromagnetite quartz buffer plus 0.5. That is the 0.5 above this buffer log units. Is for the rocks is magnetite bearing is a normal I type. So the minimum log oxygen fugacity value can be obtained for the normal I-type granitoids. If the log value between the buffer of -5 and plus 0.5, that indicates a coexisting of magnetite and ilmenite bearing granitoids. Usually this is contaminated I-type granites. So the mean log value, oxygen values can be obtained by using just on the this buffer line. And if the oxygen fugacity loss them up FMQ -5, that is ilmenite bearing granites, as magnetite is absent, is usually the reduced granites or S-type granites. So the maximum oxygen fugacity can be obtained using this value, is just using the delta FMQ buffer. So this, you can see the buffer nickel island oxide and the QFMQ, the difference between these two buffers is about 0.66 log units. And then we, this equations actually is obtained from the multiple linear regression analysis of all the experimental data up to 1996. It was proposed by Nikolov et al. And this is a logger is a mole ratio, and this is a T is in Kelvin, and H and K are coefficients. That is related to the alkalinity of the melt. And X denotes the mole fraction of oxide I, or like silica or potassium, etc. And D is coefficient of the oxide I. So the temperature, the melt temperature T, we're just using the zircon saturation model. And then this value, log value, as I mentioned before, based on the iron titanium oxide assemblage. And then the mole calculation and all the composition, you can know you calculate it. So you can get the mole ratio. And we present a combined Excel a spreadsheet program to get this calculation very readily be carried out. And then we're using convert this total number to the adjusted number, and using this estimated ferric and ferrous iron oxide ratio content to calculate CIPW normative compositions, and then we can get improved crystallization pressure estimation based on the quartz pyrometer. Now I show you how this works using the show this diagram we get. Yeah, this is the spread, consists of 5 spreadsheet as linked by the mathematical equations. And when you put your samples, the whole rock analysis, here, you just put it in. And then you, based on your iron titanium oxide ratio, you can get the oxygen fugacity buffer, like delta FMQ value in this sample, because it is the magnetite bearing. So I use 0.5 here. And then when you put the data in, you just click on the saving. And then you go to the spreadsheet table 1. So you automatically get calculated for the ferric and the ferrous iron oxide. And also this spreadsheet just showing how the temperature calculated based on the zircon saturation model. And this is just how you convert the delta value to a real value. I mean, and the spreadsheet is CIPW calculation that's based on the ferric iron oxide ratio, just a number. So finally, you get the result you want, and you also get the pressure estimation. And if we assuming the density of the continental crust is 2.7, you can get the depth of the granite intrusion. So now you know how much rocks overlying on the intrusion is removed from this, like 7 kilometers over the current level, erosion level. So if the granite age is determined, so you also can estimate the erosion ratio of the granitoids. Okay. Now it gets back. Yeah, this is the calculated result. I just said, based on that spreadsheet calculation, and it is the result. So I use this method to estimate the granite crystallization pressure in the southeastern Manitoba when I do the granite project for the survey. And when I do the survey, I try to use the Humboldt aluminum in Humboldt jabometer, but most of the Humboldt actually are altered. And so that's why I try to find out other way. So this has come up some kind of the gyrometer we proposed. And using this method, you can see the different, I just showing some of the S-type granitoids that is situated in the boundary of the terrain boundary zone or close to the terrain boundary zones. That is pretty low pressure. And for instance, in this is overlapped. Okay. I show you here. Yeah, I just show small. This in the terrain boundaries. You can see the Pluton 5 is actually the TTG suites, and in between it's the English River and Bird River greenstone belt that is S-type granites. Actually, all the felsic S-type granites is crystallization pretty low, up to 217 MPa, and also the others the same. I mean, very similar, very low. Okay, I do the again. Okay, now I'm going to switch to talking about a little bit. The key of using the barometer is to adjust if the granite melt are saturated in water. And that is the key. And we can, based on the field observations, textures, and then we know if these granites melt is or saturated with water. And I use a few examples. And this is from the Mountain Pleasant in New Brunswick. And we can see some micro graphic textures, and also some murmuritic textures, and some this very beautiful quartz phenocryst in the seated in the fine grain, the felsic ground mass. And you can see some erosions on the edge of the quartz that indicates the the melt are saturated with water. And also this is more clear, the same similar texture is erosion of the quartz. And this is also this is the muriatic cavity is from the Mountain Pleasant phase 3 granitoids that also indicate the granites are saturated with water. And also using the unidirectional solidification textures. And this is from the States, the Blue Hill granitoids in Nevada. And you can see beautifully the quartz C-axis is pointed to the growth direction from the wall of the dike until to the center of the dike. And that is definitely indicate the melt is saturated. Also the on the field associated apatite or pegmatite is another indication. Also, we also can base on the mineral assemblage of the sample on the outcrop. And this is a Tar Heel granites is a massified garnet bearing. And this is from Lake George granites, also from New Brunswick. You can see some of the phosphate biotite phenocryst in the sitting in the fine grain, the felsic ground mass. Also, we can use the fluid inclusions. This is interesting. Is the acular apatite crystals entrapped are enclosed in the plagioclase phenocryst, and you can see the the fluid inclusions is the gas vapor inclusions. And then when you do heating and do the density estimation, you can also give some of the pressure. But this is likely to a hydraulic rather than the lithostatic. And also the similar is the barrel from the pegmatite is a multi-phases of inclusions. So based on all this evidence, you can know the granite intrusions at whatever, usually at a later stage, are approach water saturated. So we can, using these samples, and then apply our quartz barometer to estimate crystallization pressure or emplacement depth of intrusion. So far, we talk dealing with all the geochemical aspect, but when do this emplacement processes of granite? I'm not touch this too much because there's many literature published already. But this I talked to Dave. This is another topic. So for PhD, but we have to consider a few factors like the current geometry of the intrusions, and that we can know the erosion level. Again, it's crystallization pressure is fundamental. And also we need to consider the physical properties of the granite melts, the density, viscosity, and water solubility. And also this thing basically is related to the chemical composition of the melts. And also we have to consider the passive versus active emplacement, and like the dike pumping or doming, that's based on your mapping work. And also you considered the knowledge of the constant crustal. That's usually a ductile or brittle, depends on the depth of your intrusion, and the structural settings. That is like deep faults, shear zones that link to the tectonic regimes, and extensional or compressional setting, and how these magmas arise from the source region to the emplacement site. That is you have talking about the structure. Also, there's some research on the constraining from the numerical modeling by using a proper boundary conditions. All this considered can give you a big picture how the granite intrusions in placed processes. I will not touch this too much. We know the if the and just evaluate the granite intrusions mineralization potential. So we need to know the petrographic types and degree of fractionation and the redox conditions. This is the key to adjust to assess the mineralization potential of granite related all deposits. And from here, we know some of the metals, their behavior differently in the granite systems. Like tin 4+ substitute for the titanium 4+ in magnetite or ilmenite or biotite under oxidized conditions. So the tin 4+ is compatible during the evolution in oxidized melt, but tin 2+ is incompatible. However, under reduced magma conditions. So that's why the buildup of tin in magmas is preferred by reduced magmas. Also, the moly oxidation states are incompatible, but the low moly oxidation state are compatible with the titanium substitution. So the buildup of a moly usually is preferred by oxidized magmas. For copper, they required the oxidized because the 2+ copper is partition into the sulfide if the melt is reduced. So they prefer the highly oxidized magmas. So we know the behavior of the different metals behave differently in their different redox conditions. So this is important for other things when you consider the mineral deposits metallogenesis. So we have to consider if the granites or intrusions are saturated with water, that related to the magmatic to hydrothermal transition. And if the saturated, the all fluids can exhaust from the water saturated granitoid intrusions. That depends on the environment or confined pressures. And interestingly, when you're looking at this, the all minerals precipitation that required usually why some intrusion produce all deposits, but some are not. So you have to consider a couple of factors like favorable geological setting, like intrusion related to gold system that is related to reduced I-type granites. Actually, this intrusions is intruded into like a thick, like a carbon or this all reduced carbon bearing sediments, and then that can the reaction, the redox reaction can convert the oxidized magmas to reduce that magma. And other things you have to consider the redox condition, reswitch I called, and for example, reduced magmas to relatively oxidized or fluids to deposit like a tin mineral casterite in tin deposits. Because it's built up, you need a reduced condition, but when the mineral precipitation, you need elevate the oxidized condition. Similarly, for the oxidized magmas, for the porphyry, you build up, you need the oxidized magma, but when you precipitate, you need a little bit reduce. Oh, that also, besides that, you also have some kind of temperature or other pressure control that is affect the metals complex in the fluids. When the other physiochemical conditions change, this solubility will change. But the redox are more important. So other things we consider the TPOX conditions of the fluids. So I just give you two examples. One is a tin. A tin deposits, you can see the Greisen veining is absolutely related to a highly evolved or fractionated late granitoids. You see all the granites is not mineralized, but the later stage highly evolved is mineralized. This is the copper deposits from Nevada. And you also can see all the deposits, porphyry deposits occur at the apophysis of the later stage granite intrusion called the low hill granites. And this is also indicate a highly evolved fractionation are more important for the copper granites, copper deposits. And also you need some kind of redox switch. And you see the older granites and then younger granites. This is the oldest, the younger, and then the youngest. All the fluids, releasing from the progressively cooling from the depths. So that along all the structures, all these kind of the points actually is the faults. Finally, I just tell me these conclusions. Crystallization pressure is the key parameter for the mineral exploration that genetically related to the intrusions. So when you applied this parameter, it is should be the water saturated, and that can be assessed from the field texture mineral assemblage or associated applied or pegmatite. The redox conditions exhibit considerable influence on the estimation for the metaluminous to moderate poor aluminous granite systems, especially for the silica low granites. But such redox condition, however, on the pro-alkaline granites or highly evolved granites may not be considered. So also we present the spreadsheet to calculate the pressure to improve. Thank you very much for your patience.
Thank you, Xue-Ming.